1. Can you detail the specific problem that specialized sparse autoencoders, SSAEs, are designed to solve, particularly in relation to the limitations of existing sparse autoencoders, SAEs, when capturing rare or tail concepts?
Specialized sparse autoencoders, SSAEs, are designed to address the limitations of existing sparse autoencoders, SAEs, in capturing rare or tail concepts within foundation models, FMs. While standard SAEs aim to capture a wide array of concepts from general-purpose data, they often miss infrequent or specific concepts due to their reliance on the frequency of activation, leading to a significant amount of dark matter features that remain unrecognized. SSAEs tackle this issue by focusing on specific subdomains, allowing them to efficiently extract rare features without the need to scale to billions of features, which is impractical. By utilizing a targeted approach and employing techniques like tilted empirical risk minimization, term, SSAEs enhance the representation of tail concepts, achieving a 12.5% increase in worst group classification accuracy on the bias in BIOS dataset. This targeted methodology enables SSAEs to capture a greater proportion of tail concepts compared to standard SAEs, which struggle to generalize to rare features due to their broad training on general datasets.
2. How does the proposed method of specialized sparse autoencoders, SSAEs, work? Please illustrate the step-by-step process of training an SSAE, including the use of seed datasets and the implementation of tilted empirical risk minimization, term.
The training process for specialized sparse autoencoders, SSAEs, begins with the selection of a small seed dataset that contains specific concepts or limited data from the target subdomain, such as toxicity. This seed dataset is then expanded using high recall retrieval strategies, like dense retrieval or track and re-ranking, to identify and retrieve relevant examples from the foundation model's pre-training corpus. Once the subdomain relevant data is curated, a pre-trained general-purpose sparse autoencoder, GSAE, is fine-tuned on this dataset, allowing the SSAE to specialize in learning features that may be infrequent in the general domain but prevalent within the target subdomain. Additionally, during this fine-tuning process, tilted empirical risk minimization, term, is employed to adjust the training objective, emphasizing the learning of rare tail concepts by minimizing the maximum risk rather than the average loss. This approach encourages the SSAE to capture a broader range of features, particularly those that represent rare, domain-specific concepts, enhancing its interpretability and effectiveness in detecting tail concepts.
3. Provide a concrete example that demonstrates the inner workings of the SSAE algorithm. Walk through the training process using a small seed dataset and describe how it influences the feature extraction for a tail concept.
The specialized sparse autoencoder SSAE algorithm begins its training process with a small seed dataset, which consists of specific concepts or limited data from a target subdomain, such as toxicity. For instance, if the seed dataset includes examples of toxic language, the SSAE uses this data to identify and retrieve relevant examples from the foundation model's FM pre-training corpus through high recall retrieval strategies like dense retrieval. This curated subdomain data is then used to fine-tune a pre-trained general-purpose sparse autoencoder, GSAE, allowing the SSAE to specialize in learning features that may be infrequent in the general domain but prevalent within the toxicity subdomain. As a result, the SSAE effectively captures tail concepts, rare features associated with toxic language, by focusing on the specific characteristics of the seed dataset, which enhances its ability to detect and represent these elusive features. This targeted approach leads to improved performance in identifying rare concepts, as evidenced by the SSAE's ability to achieve a 12.5% increase in worst group classification accuracy on the bias in BIOS dataset when used to remove spurious gender information.
4. What empirical results support the claim that SSAEs outperform standard SAEs in capturing rare concepts? Discuss the significance of the reported 12.5% increase in worst group classification accuracy on the bias in BIOS dataset.
The empirical results supporting the claim that specialized sparse autoencoders, SSAEs, outperform standard sparse autoencoders, SAEs, in capturing rare concepts are demonstrated through a 12.5% increase in worst group classification accuracy on the bias in BIOS dataset. This improvement indicates that SSAEs are more effective at identifying and mitigating spurious gender information, which is crucial for ensuring fairness in model predictions. The SSAEs achieve this by focusing on subdomain-specific features, allowing them to capture a greater proportion of tail concepts that standard SAEs, trained on general-purpose data, often miss. Additionally, the methodology employed in SSAEs, including the use of tilted empirical risk minimization, term, enhances their ability to learn features that represent rare concepts, further contributing to their superior performance. This increase in accuracy is significant, as it not only reflects better model interpretability, but also highlights the potential for SSAEs to improve AI safety and fairness in applications where rare features are critical.
5. Explain the validation methodology used to test the effectiveness of SSAEs. What datasets were employed, and what specific metrics were utilized to assess performance?
The validation methodology for testing the effectiveness of specialized sparse autoencoders, SSAEs, involved evaluating their performance on two distinct datasets, the physics archive dataset and the pile toxicity dataset. For the physics experiment, a seed concept dataset of 9 2K tokens was expanded to 13 9M tokens using various data selection strategies, including dense retrieval and BM25. The performance of SSAEs was assessed using metrics such as L_0, which measures the sparsity of the model by counting the average number of active features, and perplexity with SSAE, which evaluates reconstruction fidelity by calculating the average cross-entropy loss on an evaluation dataset. Additionally, the models were tested on both in-distribution and out-of-distribution test sets to gauge their ability to generalize beyond the training data. The results indicated that SSAEs trained with dense retrieval consistently outperformed those trained on the full OpenWeb text dataset, demonstrating their effectiveness in capturing rare domain-specific concepts.
6. What limitations or potential drawbacks exist with the SSAE approach, particularly regarding its reliance on subdomain data selection and the implications for generalization across diverse datasets?
The SSAE approach has notable limitations, particularly concerning its reliance on subdomain data selection strategies. While the method effectively captures rare features within specific subdomains, its performance heavily depends on the quality and relevance of the selected training data. The paper indicates that while dense retrieval consistently outperforms BM25, the latter exhibits poor out-of-distribution generalization, suggesting that SSAEs may struggle when applied to datasets that differ significantly from the training subdomain. Additionally, the findings reveal that multiple passes on seed data during SSAE training can lead to overfitting, which further complicates generalization to unseen data. Consequently, while SSAEs enhance tail concept detection, their effectiveness may diminish when faced with diverse datasets that do not align closely with the curated subdomain data used for training.